Bob, are you ready?
Yeah, we're ready here, Don.
Okay. Well, thank you for joining us this afternoon. We'll be covering four more of our topics for the National Road Research Alliance, long-term research on the projects that are started up initially. And again, we had four this morning, and we have four this afternoon. This afternoon, from 1 to 3 o'clock, we have some discussions right now about the HMA overlays that were done a couple of years ago. We had some work on the early opening of concrete pavements at 1:30. 2 o'clock, we'll be looking at the joint repairs that were done. Brown Intertech's looking at that. Then American Engineering is going to be talking a little bit about the cold central plant recycling efforts going on. So that's what's happening at this morning. The format will be 20-minute talks with some questions after that. So again, we have four presentations and we'll get in going pretty good. I noticed that we have many of the same people online. So again, thank you for your participation. Really appreciate that. And with further ado, let me get into introducing the first speaker. Eshan Dave has worked both here at the University of Minnesota Duluth and now he's at the University of New Hampshire, but he's working on the long-term project for the flexible team related to developing best practices for rehabilitation of concrete with HMA overlays and also looking at density and reflective cracking. So Eshan, if you could take it away from here.
Sounds good. Thank you very much, Ben. And again, thank you to NRRA for coordinating this web-based research phase of addition. I think it's great to be able to distribute the information and be able to tell everyone the project that we are working on. So this project essentially, as Ben mentioned, came from the flexible team within NRRA as one of the long-term goals with primary focus on reflective cracking. So that's the central theme of this study. And within that theme, what the participating states as well as the associate members have asked us to do is to develop some kind of performance curves that they can then adopt in their rehabilitation decision processes, whether they use a decision tree or decision matrix or some kind of pavement management based decision approach. So what will come out of this project, and you'll see this in subsequent slides, is essentially providing what kind of life expectancy can one expect from overlays as function of their thicknesses and the types of materials that are used in those overlays. But on top of those two things, also how you treat your existing concrete pavement. So those are really three main questions that will help drive not only what kind of lives you'll get, but over that life, what kind of reflective cracking performance that these agencies can then realize. So on this slide, it's pretty basic. I'm sure the audience here is very familiar with what is reflective cracking, but just for completeness, I put this slide here. So it really is just giving you classical definition of reflective cracking, and then on right-hand side you can see a very good example where you see these very straight transverse cracks that have formed in your asphalt overlay right on top of where the existing joints are, in this case in the underlying jointed plain concrete pavement. Usually the cause for these are a combination of both your traffic and thermally driven movements that occur at underlying joints and cracks, and then these movements really are causing very high level of stress concentrations in your asphalt overlays, leading to their fracture. The challenge with reflective crack is because of this excessive movement at this location, these cracks have tendency to deteriorate at a very high rate. And also they provide for another pathway for water to infiltrate into your pavement structure that continuously degrade your ride quality, because now you have potential for ice wedges to form underneath these cracks leading to tenting type of effect. And also free edges in asphalt are not good because unlike concrete, it's not able to support that free edge, and you would have a continuous degradation that would really lead to a very high roughness in your pavement. So this project itself, you can see the objective of the study as shown here on slide, and we tried to highlight some of the key words by making them bold. So really the outcome is going to be a decision tree tool that will provide agencies and other practitioners with a way of selecting appropriate asphalt mixtures and their thicknesses as function of what condition your existing concrete pavement is in, and or if you do any kind of treatment to that concrete pavement, as in stabilizing those joints or doing some kind of load transfer retrofit prior to overlay. So that is really what we are trying to address. Now, when this project was developed, there was another topic that the flexible team was also looking at, and that is tied to in situ density of asphalt mixtures. What ended up happening was, because of the way the test sections are constructed at Min Road, and also since there's quite an extensive amount of performance testing that has already been conducted on these mixtures, it was decided that really both of these objectives, not only objective on selection or decision tree for overlay selection and reflective cracking performance, but also objective in terms of how in-place density of asphalt mixtures impact their performances, including trying some of the newer volumetric concepts to getting better densities in our asphalt mixtures. Those two really merged and ended up being this single project in which we are looking at both of these things simultaneously. And as we go through this presentation, you'll see how we are doing that assessment. So overall objectives, and I've already touched on these ones. Obviously, we want to get better reflective cracking performance from our overlays. And the consequence, obviously, of that would be an improvement in pavement life cycle cost, which is tremendously important in today's economic climate in terms of agency budgets, where we are constantly trying to stretch our investment as far as possible. But on top of that, really there are also multiple side benefits or additional objectives that this study focuses on. One of them is looking at what kind of laboratory-based performance tests are able to better capture reflective cracking performance. Obviously, there's already multiple efforts throughout US on performance tests, and including Min Road NCAT partnership, which is also looking at cracking performance tests, as well as for rutting and other distresses. But since in this project there was already a component that dealt with doing these extensive lab performance testing by all the different agencies and associates, it was considered that since we are going to have field data, might as well do this comparison and learn additional, gain or develop additional knowledge through that. We will also be looking at constructability considerations and time considerations, especially in context of various performance tests. So that's another side advantage, where we are collecting data and how long it takes, what's the turnaround time on some of these tests, and so on. Again, this is not a unique effort, as you are most likely very familiar at a national and international level. There are a number of studies that are doing this. We are just trying to provide additional information on these topics since we have access to the data. The objectives listed here, the last two in green. One is density evolution of mixes. This is a very important topic. Oftentimes we construct roadway and we pay a lot of attention to volumetrics. However, in recent years, I don't believe there have been many efforts where we have continued to track how these densities are evolving with time. And that's where we are really trying to fill in that knowledge gap in this project, where for certain newer approaches such as Super Pave 5, where you are designing your mix at 5% and then constructing at 5% air void level. We want to see how not only that mix performs, but what happens to the air void structure in that mix as time goes on. Similarly, in order to get a little bit more bitumen into our mixes or binder into our mixes, there have also been efforts to do a retrogressed air void approach where you take your super pave design and then lower the air void level to get a little bit more effective binder or a little bit higher film thickness into your mix. So that is studied in this project as well, by looking at a section that's constructed using that kind of mix. And then lastly, as I mentioned before, the overall outcome is really going to be a decision tree tool that agencies can adopt, where it takes into input your existing pavement condition and gives you different scenarios. So if I choose this material and this thickness, what is really my life cycle cost associated with that overlay decision? That's really the outcome, and that's why what we will be working quite extensively on this project in this second and third year of the project is developing performance curves that various pavement management systems can adopt. So those are the objectives. I very quickly go through pavement sections and materials. I won't spend too much time on it because many of you have seen this information before. But essentially, there are 12 different sections that are part of this study. And really what is changing between those sections, or I mean, there are multiple things, but the key things that are changing between these sections are your overlays. And they are changing in terms of thicknesses. Also in terms of mixes, and when I say mix, that's not just mix as in different air void levels, but also mixes in terms of to some extent different gradations. Several of these sections also have interlayer treatments or another asphalt layer that might be between your traditional overlay mix and your concrete slab. And construction technique as well, where several of these were constructed using spray paver, doing a thin bonded overlay type of construction technique, where you can get a higher tech coat application, and through the study then evaluate what advantage you may have in terms of reflective cracking or not. What you see on this slide is the control section, which is the standard section that you have out at Main Road. This is what the overlays are constructed on, but it's really your 9.5-inch concrete with 1.25-inch dowels, and then all different sections are on top of this underlying structure. One thing that's wonderful with Main Road facility and through this NRRA effort is that we have excellent documentation of conditions of pavement. So we already have load transfer efficiencies before construction. We had distress surveys before construction, and then obviously these sections get monitored. And that's really what's helping us do develop these decision trees, because without that kind of information, we won't be able to do it. So various cells, and I have them grouped in a way. So the first cell you see here is what I call my baseline overlay type of cell, 2.5 inches of 19 millimeter mix right on concrete, and then 1.5 inches of wear course, which is 9.5 millimeters, so 4-inch total overlay thickness, and that's what we would use more as a baseline or a control overlay. And then to compare to that, you see 4 more cells here. And what's really changing between these cells is if you see the course that's going right on top of concrete, they are all 2.25 inch. That's not really changing, but on surface, you can see these 4 different mixes where now we have our traditional 1/2-inch mix with 4% air void, design air void level. That's your standard super pave mix. And then cell 989, the only difference is instead of that standard super pave mix, this one's designed as a super pave 5 mix, where the mix is designed to have 5% air void level, and then in place density also 5% at the time of construction, as opposed to typical 97% or rather 92% or 93% 7 or 8% air void level. So lower in-place density at the time of construction, but higher air void level as a design mix. 990 is a retrogressed air void mix, so it's similar to super pave mix. However, by increasing your binder amount or especially your effective binder content, the air void is dropped 1%, and that allows you to have a little bit more binder in the mix. And then 991 is designed using this spatial number 8 gradation, so it's really a finer mix that is now part of one of the super pave gradation. So it's has a finer gradation overall. The nominal max size is still same, but as compared to your other mixes. So that really deals at how we put together mixes more from volumetric perspective. Now the next two set of cells, if you look at them, the difference here is now instead of having this traditional 19 millimeter super pave layer right on top of concrete, they actually have different type of treatments prior to application of your 1.5-inch wear course, where 992 has a 1-inch highly polymer modified interlayer, versus 993 has the permeable asphalt stabilized or stabilized asphalt base course, where you are really using this low modulus layer on top of concrete, again with objective of that layer being able to take in a lot more strain or deformation without translating those into overlays. And then the next four, 984, 985, 86, and 994, those are all actually focusing on tech coat and construction technique, where they are all 1.5-inch overlays but placed with different application of the tech coat between your concrete and asphalt layers. And also in case of 986, that one is actually placed with a spray paver doing a thin bonded overlay or a bonded overlay with a high shot rate on your tech coat emulsion of 1/10 of a gallon per square yard, versus 84 more traditional shot rate of 0.08, 85 a lower than traditional rate, so 0.05, and these are undiluted rates, so rather diluted rates, so the actual emulsion amount is even lower, but this is with dilution. And then lastly, cell 995, this one is a true ultra thin bonded wear course that has a very high tech coat rate of 0.2 gallons per square yard. And in that case, actually, the tech coat is also polymer modified emulsion, so emulsion made with polymer modified binder. So those are different cells, and that obviously is going to help us populate all the information that we need towards developing these decision trees. Research tasks itself, so it's really 8 different tasks. We are still in the early part of project. We finished literature review, submitted it. You can access it on the NRRA website. Task 2, we are collecting data on performances of these overlays. We already have lab testing data from all the different partners who have tested these mixes. Task 3 is we have started to do groundwork on it. Officially, it kicks off at the start of next year, and that's where we will be making mechanistic models of these overlays, and then calibrate those models using MinRoad data to make sure that they are reliable. And then we will be able to do a lot of what if scenarios, saying that, okay, what if I increase my overlay thickness by 1/2 inch, or what if I reduce it by 1/2 inch but use some kind of polymer modified mix, and so on. So that's where we will develop large enough data set to be able to feed into your tasks 5, 6, and 7, which is where the decision tree essentially gets developed. 5 is the critical one, and then 6 and 7 is more of building tools that uses that knowledge. Task 4 is that side or parallel project where we are really looking at, for these mixes, especially the ones designed in a different way than super pave traditional approach, how does asphalt density change with time, and what impact that approach has on reflective cracking performance. So lit review, I won't spend a lot of time. As I said, we have already submitted this to the to the flexible team, and you can go online and learn more about it. But really, we looked at all different models and tests that are out there for reflective cracking, and also did quite extensive review on what these enhanced density approaches are doing. And essentially, we reported on work that's been done extensively in Indiana, where they are seeing very good responses with Super Pave 5 approach in terms of performance of their pavements, not just for cracking, but also from perspective of durability. Reflective cracking, as we know through Pavement ME and the NCHRP project associated with that, it is a challenging problem and does require quite extensive mechanistic approach to be able to simulate it and be able to predict performances reliably. So we are taking approaches that are similar to what were done in initial development of Pavement ME with certain variations. And I don't really have time to go into those in this presentation, but I'd be more than happy if you have questions or if you want to contact me on those points. On LCCA side, obviously, as you are probably familiar, there's a lot of recent work on this topic. Especially, it got kicked off with the NCHRP 1-45 study that showed that fuel efficiencies of vehicles depend extensively on pavement roughness. So our approach here is going to be really starting with FHW, a real cost software that allows you to incorporate all the different effects, but we are also keeping track of cutting edge research on this topic, and we have internal projects as well going on this topic that allows us to have a better handle on user cost. That includes things like user delays and crash propensities and lost revenue for businesses and so on. So we will be bringing in those components in the LCCA module as well. Just a quick list of all the different mix tests that have been conducted on these asphalt mixtures at Main Road. And again, this is something that you probably have seen before, because I think Ben and others have presented this information multiple times to people interested in NRRA activities. But just to bring things up to speed, everything that's shown in green is already tested. We have data. Things in orange are currently being tested, and then there are certain additional tests that got added later on. So we will be receiving some of these results. Obviously, the UNH one, that's part of our contract, so we will be doing the other ones depending on how much time and mix and so on is available to agencies and associates. They may or may not happen. How we are comparing these mixes to performance, and also mixes to mix these performance properties to mix properties such as volumetrics. We are relying on statistics, and specifically a technique that we are using is a Pearson's correlation coefficient or Pearson's correlation matrix approach. It's really a very simple technique that statistically looks at what impact one category of variable has on other category of variable. So for example, what impact effective binder content has on any of the performance properties that we saw on previous slide. And it's very straightforward. If your correlation coefficient is positive, that means as one increases or something on X increases, the Y also increases, and vice versa. 0 means there's no correlation between those two properties. These are very early results. I don't want you to really go through or get bogged down on all these numbers on the slide. I'll just focus on some of the key points that I have at the bottom of the slide. And if we look at these, what we are learning, that if you look at effective binder content, as this property increases, what we are seeing is that in general, overlay tester results and indirect tensile strength, and this is again ITS at 25C from TSR, it's not the super pave IDT at low temperature, but those properties are decreasing. So that's somewhat counterintuitive, because typically you'd expect higher binder content to have better performance. What we are also seeing is tests for durability, such as MIST and TSR, they increase with binder content, not necessarily surprising. And also things like DCT fracture energy and Hamburg results on rutting, they were both improving with increasing effective binder content. On the air void side, we saw that increasing air void was resulting in lowering of your durability, which also makes sense, but also lowering of your fracture energy, versus on overlay tester side, increasing air void was resulting in improving of overlay test results and indirect tensile strengths. So that's, again, it's fairly early, so I don't want to spend too much time on those, because really what we will be doing is making these type of comparisons between field performance and these properties, rather than these properties and volumetrics only. I just have a couple more minutes and just few more slides, so I'll go through these fairly quickly, but just some more results from lab. So what I'm showing you here are dynamic modulus or complex modulus results. This is just to demonstrate the extent of data that we have. I'm not really trying to make any points here. But if we look at the next slide, this allows us to look a little bit closer as to what happens to these mixes as we change certain things. So if we just focus on these bottom left here, we are looking at stiffness at different frequencies for all half-inch mixes. The main difference between them is the air void level or design air void level change. And we more or less see what we expect. So as we go from 3% to 5% air void levels, in general, the stiffness of these mixes is decreasing. So nothing surprising, as expected. It's always good to see that that confirmation. We are also using tools like Black Space that recently FHWA has also been started to promote for using performance-related specifications. And this is really a good way to look at full linear viscoelastic characterization of mixes. Again, this is more for demonstrating the breadth of the data. So I am not trying to make any specific conclusions on this one slide, but allows us to look at all these data in different ways. So just wrapping up, what are we doing now? So right now we have a survey out to all the pooled fund states that are member of NRRA, and what we are trying to collect is all the information that we can get in terms of how they currently design their overlays or decisions that they use. If they have any performance data, we will need cost data for life cycle cost analysis, and also getting more information on their correct contact people, because it's not usually same person who has answers to first 3 items here. So we are also collecting that. So if you are a member state and you are here on webinar or listening to it afterwards, if you have not filled the survey yet, we would really appreciate if you could fill it up in next few days. We are really trying to get the survey wrapped up before end of this year in order to make sure that we stay on time. So what I'll do is just go to the last slide here, which is just summarizing what's already done. So task 1 is complete. Task 2, majority of data we have available, and we have started to conduct the comparisons. But where we really need help from NRRA is to make sure that you please fill up our surveys that we have sent to you, so we can continue to move on towards the decision tree setup. We do work quite closely with MinRoad staff and coordinate with them all the field performance collection. So that's going great. But again, one thing where we could use some additional help, or if you know of someone who's part of this project, please ask them if they've filled the survey yet or not. So that's all I really have, and if you have any questions, I'll try to answer them.
We don't have any questions.
All right, thank you, Eshan. Any questions, Bob?
No questions online. Anybody in the room?
And I did get note from Dave Van Dusen, so I do have a correction that I'll make in the map with different cells. So we'll take care of that. Thank you, Dave.
That's pretty good. You can read your emails while you talk.
Yeah, try to.
Multi-talented guy. I guess, again, you're just to kind of highlight what you said, Eshan. This study and other studies that NRRA is doing is trying to not only utilize MinRoad data, but trying to get at the whole aspect of what states are doing, and that's where the surveys come in. And so important to get that information to make this study as good a study as it can be. So just kind of backing up Eshan for that request for data is very important.
Thank you very much. Yep.
All right. Yeah, nice.
stop presenting, and so you have the control back.
Alrighty. Thank you for your presentation and your team's efforts in this area.
Thank you very much.
And again, if people are interested in being a part of this, there's a tab that people can get on. And these presentations will be put on to our project websites for NRRA for under each project that's being reported on. For our second presentation that we have this afternoon, we are going to be talking with Lev Khazanovich from the University of Pittsburgh. He's looking at the work that's being proposed by the RIGID group, looking at the evaluation of long-term impacts of early opening of concrete pavements. And this was our test cell 24 on the low-volume road, which we drove on quite early. And he's going to talk a little bit about the progress in that study and what they're finding from both the instrumentation and observations in the field. So if Lev, are you ready to give your talk? You can get started.
Yeah, just, okay, let me. Okay, can you see it?
It's loading. There it is.
Okay. Well, good afternoon. Thank you for the opportunity to give me an update on the project we're currently working on. It's a project proposed by the RIGID team, and we're dealing with the evaluation of long-term impact of early opening of concrete pavements. In the previous project for MinDOT, we developed a model that is capable of evaluating long-term damage from opening to traffic in the first few days, but the models needed to be calibrated and validated, and this study provides an excellent opportunity for this. Well, let me start from reminding you that the current spec, it says that the pavement can be open to traffic when the concrete reaches 3,000 psi compressive strength, or like flexural strength from 350 to 500 psi, or 7 days. But basically, these criteria are overly conservative. We know it, and actually the Portland Cement Association proposed different guidelines and say that it's, especially for low volume traffic and for strong subgrade, you can have a flexural strength of 300 psi, and that should do the work. But all the previous works were made on with old mixes, and there was very little experimental verification for that, especially full-scale verification. And MinRRA opportunities, MinRRA provides an opportunity to really verify it. Like under the previous project, we evaluated flexural strength data, database collected by MinDOT, but very instance. And and this slide summarizes the effect of age on mean flexural strength of the beam, and you can see that even after 1 day, the mean flexural strength exceeds 350 psi. So basically, according to ACPA criteria, after 1 day, the pavement can be open to traffic on the majority of the cases. I would like to point out for the standard deviation for 1 day strength is pretty high, because when your age is 1 day, then plus minus a few hours can make a huge difference. Plus, in general, variability in strength is quite significant. So so that brought us to this study initiated by the RIGI team, and the objective is like evaluate visible and invisible distresses, both short-term and long-term, that resulted from early opening of concrete pavements, quantify the effect of early loading on long-term performance, and the most important, determine minimum strength at opening or other procedures that can be used to guide practitioners on early opening, and recommend strategy for minimizing or avoiding the early loading damage. For example, limit early loading to certain type of traffic, and postpone heavy vehicle loading to the later day, and specify how long the pavement should be closed for heavy traffic. Well, so naturally, it's there are many potential benefits from this project. So first of all, it will reduce the construction time and cost if we update and the criteria and make them less conservative. We improve user satisfaction, because longer construction time causes users delay and frustration. But on the other hand, we should not jeopardize long-term performance, and we should, and our recommendations should be valid enough. So then we will eliminate premature failure related to overloading at early ages. So as Ben mentioned, at Main Road, the cell 24 was reconstructed, and several test sections were created that all of them have the same thickness, all of them have the same dowel design, like 1-inch dowels. They're built on 6-inch thick granular base and on sand subgrade. But what they're different in the way how they were loaded, before I move it, all of them has standard slab size. It's 12 by standard width and 15 feet joint spacing. It uses standard concrete mix, and for one cell, the vehicle was driven across the pavement, while concrete was still plastic, and that caused visible damage. But four sections were loaded at early age, but after concrete was set, and one section was left as a control section. So this slide shows an example of rod created in a plastic stick concrete. Well, it illustrates that opening to traffic too early is not a good idea, but it's basically an extreme case, and just drives the message across. But in reality, the main subject of the study was to evaluate the effect of loading with two types of vehicles, snow plow and coaxial pickup truck. So this slide shows the loading pattern. First, cell 124 was loaded, and the vehicles moved back and forth. After that, both cell 124 and 224 were loaded, and again vehicle moved back and forth, and 324 and in the fourth loading, all the sections from 124 to 424 were loaded. I need to mention that the sections were constructed from west to east, from 624 to 124, so that at the time when section 124 was loaded, it's actually the concrete was much more mature than at the same time with the section 124. So basically this slide shows the pavement age at the time of loading and measured in hours. So section 124 was loaded in 3 hours, and after concrete placement, and section 424 was loaded in about 11 hours after the concrete placement. But even 11 hours, it's a pretty early age of loading. Even after dealing with this data for quite a while, I can't understand completely why section 124 is not damaged, but that's the case. And one of the explanation I found is that it's in a paper by Hammer et al. And later was discussed by Nedi and Solomon. And basically what it says that at very early age, the concrete has very high strain and capacity, so basically it can withstand significant strains, and because stiffness is low, and tensile stresses are low and tensile strength is low. But with the time, stiffness increases, so strain capacity decreases by strength increases. So basically there are two factors are fighting with each other. It's also interesting to see on this slide, which in this paper published about 10 years ago, but still, if you look at the horizontal scale, the strength is not very high even after 10-12 hours after concrete mixing. So basically about like 4-6 hours after placement, I assume. So it's quite possible that in that study they used high water cement ratio because it's easy to work in the lab. And doesn't represent current in stiff mixes used with slip form paving. But under this project, we reviewed the data provided us from Minroad and collected by Minroad engineers and technicians, and tested by Minroad or by consultants, like in this case American Engineering Testing. And this slide shows the testing of the mix that used in construction prior to concrete placement. And in this case, you see that the concrete flexural strength actually accelerates much faster than concrete compressive strength. And that is quite quite interesting, because in the literature there is no agreement what strength is developing fast. About 50% of papers say that compressive strength is developing faster, and another 50% say that flexural strength. But it looks like from in that mixes the flexural strength developing faster. But the top plots were given under more or less constant temperatures, and if we convert it to maturity, so basically it's summation of the time above reference temperature, which summation of the temperature above reference temperature for each hour, then in this case, that strength development can be applied to any temperature regime and after placement. In this case, we can convert time of loading into the maturity of loading and estimate strength here. And basically, that analysis was already conducted by MinDat, but we went back and double checked it and slightly corrected it. But basically, what we say that after that the third loading of cell 124 correspond to about compressive strength 100 psi and modulus of rupture 90 psi. So because it's a maturity about 150, and fourth loading of cell 324, the compressive strength was 760 psi, which is quite low, but the flexural strength was already almost 300 psi, and at the when the cell 424 was loaded, the compressive strength was still quite low, but the flexural strength was significantly it's quite significant, and according to ACPA criteria, this pavement should not fail. And basically, it's interesting, none of them failed, but I still can't understand why 124 didn't fail. It's important that to point that the first loadings were made at the maturity level for which we even don't have reliable tensile and compressive strength. So basically, after that, we re-evaluated dynamic strain responses provided to us by MinDat, and basically we come up with similar conclusions that that was achieved by MinDat, but with some exceptions. First of all, we make sure that we are not accounting for noise, and when we pick up maximum responses. So we applied several techniques, but the simplest one we just use moving average to find the approximate window of time of maximum responses, and after that we would find the maximum response in that area and subtract the baseline. Second, we reviewed the data and variability in data and found that if the standard deviation more than 80 microstrain, then most likely the data are not reliable. So in this case, it's an example of pretty good data. The standard deviation data is much lower than 80, and in this case, you can see pretty bad data. So they're not quite reliable, and we decided not to use this data. And this slide shows that after we eliminated all the questionable data, then we have quite consistent trends from section to section, from cell to cell. It's interesting that cell 224 shows the highest tensile strains at the bottom, but these trends are more or less consistent. But again, this cell didn't have any visible damage, and as we see later, it's kind of, even if there was a macro damage, it kind of self-heal itself. So in this case, the longitudinal strains and transverse strains have the same trend. 224 shows the highest increase, but definitely no damage. Here I would like to point out that when the measurements were taken, it was before saw cutting, so basically it's not, it's the behavior is slightly different than after joints are formed. But basically our conclusion was that very high concrete strains were measured, and here we even excluded kind of questionable data that might have much higher strains, but those strains are not led to significant damage, and that is and the explanation is that stiffness was reasonably low and tensile strength was quite high. So basically, if criteria should be used for the opening, it shouldn't be compressive strength, it should be tensile strength. And if compressive strength is used, it's only to way to estimate tensile strength. We also evaluated data collected in November of 2017, and it's interesting that in this case, cell 124 and 224 shown very similar strain level. Cell 424 actually exhibited higher tensile stresses, about 10 microstrain, but still those strains are reasonably low, and of course, as I said, there is no really significant damage. And here we have transverse strains, we have the same trend. So, so I say in this case we have observed slightly different trend from previous, but in both cases there is the strain level is sufficiently low not to create any problems. We also evaluated ultrasound tomography data collected by Dr. Hoyk for us. And first of all, we evaluated shear wave velocity, and the values we obtained confirms the estimates we got from previous studies, that basically concrete stiffness after 24 hours was where we would expect it to be. And so its velocity is about 2.4 kilometers per second, which means that the tensile strength was most likely about like 400 plus psi. That corresponds to maturity measurements, and stiffness was about a couple million psi at that time. We also tried to evaluate damage with concrete, and we used the technique we developed previously for old concrete, and we use it with. So in this case, we take an envelope of the signal and make certain transformation and calculate an area under the curve. So hide that area, greater damage in concrete, because it means that the signal is more distorted. And in this case, we found that control cell 624 does have slightly lower damage, but the damage for all cells were not very high. Maybe there's exception inside lane for 224, but even that one, we're not sure how confident we are. And if you look at the maximum index, there are several occasions for which it was quite significant. That's again for cell 24 and for outside lane of 624. But at the same time, and 524, when measurements were taken close to the rut created by the truck, were naturally in worse shape. But still, at this stage, we can't say that this damage is caused by early loading and not by, let's say, poor consolidation of concrete. Not poor, but maybe less than desirable. So we are still working on revising this index, and the reason why we're not confident this time, because when we review the data more carefully, we found that the analysis we applied maybe not adequate for the cases when velocity is much lower than for mature concrete. The index was developed for velocities about 2.6 kilometers per second, 2.8 kilometers per second. Now we have 2.4, and that might have an effect, so we might need to adjust it. So basically, at this stage we can't rule out that there is damage, but we don't have any definite answers if it's there or not. We also look at the deflection data, and those results are actually quite interesting. Looks like I'm running out of time, so I will show only a few results. But basically, what we've done, we analyzed like simple analysis, normalized deflections, and later we performed the calculation using two techniques, and we found that those results were quite strange. First of all, the variability was higher than we expected, and the second is the calculated values were higher than we would expect for a pavement of the thickness at this age. We're still trying to explain these results, and we're checking our calculations, but it looks like we're quite confident where we are. And just a few more slides. So basically, for the one of the concerns we had that early loading may damage joints. In this case, we analyzed the load transfer efficiency, and it's interesting that for inside layer that was subject to traffic after construction until this testing in October. The load transfer efficiency was about 90%, which is slightly lower than we expected for a doweled pavement at this age. But basically, it's pretty good anyway. But the results were quite strange for outside lane, and this slide shows actually normalized deflections at the pavement edge and pavement corner, and it shows interesting trend that if you compare cell 124 and cell 424 inside lanes, then the values are pretty similar and the trends are very similar. But if you look at cell 124 inside and 424, like sorry, 124 outside and cell 424 outside, then you can see that the difference between edge corner and edge displacement is much lower, and deflections are much lower. And one of our explanations that might be that just joints did not deteriorate as fast as, or maybe even didn't propagate as fast as it was done on the inside lane, and that's what we must include in our model later on when we get to them. So basically, that's what we've done so far. We went through the data provided us from MinDat. We had difficulties and we still have difficulties explaining some of them, but it looks like we're making progress out of this, and now kind of start making everything start making sense. And the most important observation is that it looks like some of the conclusions that you can find in the literature and some of the experience people have with other mixes are not applicable to stiff mixes that are used for slip form pavers. And basically our conclusion is that the current guidelines are very conservative and can be relaxed, and it's I'm not sure that we would like to recommend open traffic after 3-4 hours, but definitely there is no need to wait for 7 days for that, and of course the results should be maturity based or stiffness based, not time based. But basically, to really provide reliable recommendations, we need to conduct simulations and try to explain some of the effects we observed in the field, and that will be done later on when we start adjusting our models based on the information we analyzed so far, and that was collected at Min Road. That concludes my presentation. I would like to thank MinDat for the data and the work that they've done and data they provided. I would like to thank American Engineering Testing for their work on this project, on the the data that we used in the project, and NRRA, because that your support is crucial for this. that concludes my presentation. I will be happy to answer any questions you may have. I have
Alrighty.
maybe have 1 or 2 minutes left.
Yeah, thank you, Lev. Nice presentation. Bob, do you have any comments or any questions online?
Don't have any online questions? Anything in the room? Looks like we're good for the room.
I guess, Lev, we paved this test section and it was pretty warm that day.
Yeah.
I mean, how does that kind of hurt the research going on, or does that help, or what's your thoughts just on that initial, weather that we just happened to have that day of paving?
Well, on the one hand, it helped because actually it provided more extreme case, and it's like time-wise, it's very impressive because after a few hours, the strength was quite significant, and that really shows that time-based guidelines can be quite meaningless. But on the other hand, it created some challenges. As I repeat already several times, I still don't have good explanation why cell 124 did not fail. And that bothers me, and I'm not sure that I will be able to explain it even at the end of the project. But it just didn't want to fail. Period. And in my opinion, it had to fail, but it did not. So.
Right. Yeah, I would have thought we would have had a failure, early on, at least for the initial start of the loading. But
yeah.
Like you say, we didn't. With that, I guess we are out of time here. But thanks again, Lev, for your work and your colleagues that are helping out with this project.
Okay, thank you.
Then we'll get the other project on the screen, and I'll do the introductions. Let me just bounce to it. Our third speaker for this afternoon is going to be Justin Lashley from Barana Intertech. They are working on the long-term research effort for the pavement maintenance group related to the effective long-lasting partial depth repairs, joint repairs for challenging conditions. And this is where we took a stretch of our old westbound that we built Min Road next to, and we came up with common repairs that they went through, and we went through and put different types of materials down. But Justin will be talking about that, and we're going to see some results from this fairly quick because we are seeing some of them not lasting as long. But again, this was a short-term research effort because this was kind of what can be done short-term to get some short repairs done for the roadways. So again, we have lots of traffic out there on 94. And with that, Justin, go ahead and do your presentation.
And Ben, can you hear me all right?
Can hear you just fine. Thank you.
So we'll get started here. This is the a typical cell installation. You can see all the different type of patches. These patches were basically man-made with a milling machine. So a little deeper than what we had expected, but they did a very good job of creating these different patches, either along the center line or wheel path. As you can see, there were several types. And the installation, which was back in 2017, say September, maybe early October timeframe, 16 different products, various suppliers. There were a couple products that were by the same supplier where they wanted to try a couple different things. We had everything from what I'll call conventional high-early concrete, package material, epoxy products, some HMA products, and then some in that conventional concrete there were steel fibers to see how that performed. So the first winter, the site visit did about Memorial Day, and at that point one material was considered to have failed. And I have a lot of pictures here. That's kind of what my presentation is. That's what really tells the story. So we'll kind of get into that here in a few slides. The other big thing was some of these epoxy products can be pretty slippery, so they put some broadcast aggregate on there. Most of that was gone on a lot of the patches after the first winter, but several patches had some drying shrinkage cracks, probably manifested shortly after it was placed. Not a big deal, but just something worth to note. The majority, other than one product, everything looked fine. looked like it was, a lot of it looked like it was placed 2 or 3 weeks before this visit. So I was pretty surprised by that, and I'll have that in my wrap-up slide there, why I was surprised by that. So again, typical shrinkage cracks. Hopefully you guys can see them on your screen. Would kind of expect this for some of this product. It's high early, sets pretty quick. And again, with the size of these patches that they were, wasn't surprising to see this type of cracking. Nothing to be concerned about, pretty typical, not too worried about it. This was the cell 94008 after the first winter. This is just one of the patches, but basically it's coming out. It's highly cracked. It's got an issue, and why that might look like HMA, it is a asphaltic product, but it's called Aqua Patch. So basically you kind of pour it in there and pour water on it, and it's supposed to fill that patch, but did not survive the winter. So went back out there in June. Again, there wasn't much going on after the first winter, so not a lot to talk about there. How they look in June. Again, starting to see some cracking that's not related to shrinkage cracking. Some patches are starting to spall a little bit, but on the whole, it still looked fairly good. Wasn't a whole lot going on, but you can see some stuff start happening. So again, here is a crack that's not a shrinkage crack. That's what I'll call a mechanical crack. It's that starting to work there and starting to break off. It hasn't spalled out yet. Wouldn't surprise me if that does spall out, but you can seeing some deterioration starting in some of these patches. Again, there's another one. That's not a drying shrinkage crack. That's a mechanical. It's starting to work. I'm interested to see how this crack basically proceeds through time, because you might be able to see it, but this is one of the material that has steel fibers in it. So I'm kind of surprised by the size of that crack with that steel fiber in there. But again, if you look at some of the installation pictures, and I'm going to use the term undermining, this pavement is getting pretty old. There is some pretty big voids under the pavement where it could pump. So repairing some of these joints might just be tough for some of these products. The product might be good. It just might be time for a full depth joint repair in some of these areas. And I think that's what's happening here. Again, that's kind of my opinion, my theory. But that's something we're going to watch, is that it's just there's no support under the concrete pavement in this area. Excuse me. And again, here there are some shrinkage cracks, but you see some kind of cracks there on the gray material over on the right, what I'll call the spider web. Those weren't there previously, so just kind of showing me something's going on there other than the shrinkage cracks that were there shortly after it was placed. But again, no spalls on this patch or this product yet. But here's one kind of where we starting to see some stuff start happening in June. So I am getting some spalling there. That I didn't knock that out with my hammer. My hammer's just there kind of for a scale. But when I went out, we're seeing some deterioration in some of the patches. And you can kind of see just a long shot there. But again, is some of this because it was feathered instead of having a nice, what I'll call thick, or a 90 degree or 45. Maybe the feathering led to this deterioration. We don't know at this time, but again, from May to June, we're starting to see some stuff happening. How about June to September? This was the shocking one to me. This is, as you can see here, we saw it just kind of took off. The wheels came off, started to see a lot of failures. And these weren't small failures. These had to go out and repair the repair failures. There was some pretty big dangerous stuff going on with the size of the spall and the size of the patch and material not being in there. So this is kind of between June and September is when things really started showing and manifesting as large-scale deterioration. So you can see here's one product. And again, with the size of these patches that were made, we had to kind of mix and match some, just because some suppliers didn't have enough material. So on your left, it's not a repair. That's just a different product there. And then as we go right across that longitudinal join, that was a patch material that went all the way into that patch. But as you can see here, that right side of that has been repaired because it's gone. So there's one we kind of see that, oh, it's starting to go and it's starting to completely come out of the patch. It's not remaining in there. It's debonding and being lost. And this was a really interesting one. That's a transverse joint there. Half of that patch material, it's just gone. And when we were out there, so obviously we make a phone call and say, hey, before traffic's turned over, this one's got to be repaired. But I don't know how to explain. Half of that's out, half of it's still in there. That prep of that patch was exactly the same on both sides of that transverse joint, but some of that material is coming out. And what this material is basically you throw 3/8 aggregate in the patch, and then you kind of have think of it as a garden hose pouring epoxy into that aggregate. Which the reason I'm detailing that is this is that same material, and it's almost like the epoxy is coming out of that patch, as you can kind of see that sheen on top. So again, there's just one thing we're noting there is maybe that epoxy's, I guess for lack of a better term, leaching out of that patch, which might be why it's failing the way it is. And again, just some more repairs here on this product. You can see the size. It's not small pieces. We're talking it's half the size of the patch that's having to be repaired that was placed in 2017. And some of this is repaired by other products that were kind of left over. This, I believe, was what Jerry calls blow patching to repair that. So again, we just saw a lot of deterioration kick off after June. And again, wide scale repair there where the material is just no longer there. So what have we, or I should maybe say I, learned so far at this point? The winter wasn't harsh for the patches. I really thought I was going to see a lot of deterioration due to obviously our winter weather and snowplow effects and things like that. And kind of after we were having a little meeting to discuss this, and what we kind of came to the realization is that part of 94 is probably not snowplowed quite like the rest of the interstates. In the wintertime, there's not a lot of switchovers, so it doesn't get the plowing with our light snows or our de-icing chemicals with the light snows. The biggest thing is a lot of these, what I'll call whole-scale patch failures, I don't think it's material related as far as, the material's not a good patch material. And we've documented this. The sandblasting is the biggest factor, where a lot of the failures are occurring where it was not sandblasted. So if you can kind of picture what I'll call the driving lane and the passing lane, the driving lane was sandblasted for some of these cells, and the passing lane was not. And the driving lane looks fine where it was sandblasted. But where it was not sandblasted, that's where a lot of the patches are basically coming completely out. They're not bonding to the concrete there. So again, for repair material, surface prep is one of the most important things. And we're seeing here that it does make a difference out on the road, whether how the surface is prepped before you apply the repair material. And that's basically what I have so far. Is again, I could show you 100 pictures of the patches, but I tried to pick and choose of what we're seeing happening and what's going on. And again, in some of them, it's nothing. It looks like the day it was placed, but as you can see, some of them have to be fully repaired.
Thank you, Justin. A couple questions, I guess, related for you. One of them is let's see, how many years are left in your efforts for viewing these products? You're going to look at them?
Today, this was the first year, so it should be 2 more years.
Okay, because I know out at Minroad right now, we've been doing some repairs in those areas also. So did you get a chance to look at them this fall quite yet?
September was the last time I was out there.
Okay, sounds good.
And that's a good point, Ben. Those repairs with the blow patch, I believe that's been done by, I'll say the Minroad facility or MnDOT personnel.
That was MnDOT personnel, yeah. Any questions online, Bob?
Yeah, there's a question from Tom. Said, since the underlying joints are so wide, do you think the closing of the joints in the summer are the primary cause for most of the failures?
No, it's underneath the concrete. So there were some places where, again, the visual I used, so you have the patch along a transverse joint where I could go, if I could get my fist under there, there's like a fist-sized void under the concrete pavement. Does
Right.
that make sense? So
Yeah,
the concrete pavement's been undermined.
say it a different way is that a lot of the old I-94 that we have out here is from 1973, and that's had a lot of traffic on it. And a lot of those joints look pretty good from above, but once you get down below in the lower parts of the concrete that's touching, say, the granular base below, that's where it's kind of rotted out. So again, it's kind of undermined, like was noted. Any other questions that we have,
And
Bob,
Ben,
or in the room? Or
I don't know if
respond
this
to that?
was. Oh, and Ben, one comment that just had something to pop in my head here. I don't know if this was a nationwide study or if it was MnDOT, but when they went out and cored some joints, and it was like you were saying, what I'll call joint rot. And what they were seeing is some of those joints were rotting from the bottom up on some of these older, higher water cementitious pavements. And that's kind of what I think is happening out there, is that joint rot's happening from the bottom up.
Correct. Any questions or comments? Bob, anything in the room there?
Nope,
Amanda?
we're clear here.
Okay. Yeah, there's a lot going on. Again, this study was kind of a second part of a study where initially we had some test sections on our main line, I-94, and we did a bunch of different types of repair mixes, but we ended up having, it's hard to tell which mix was working in what way because they're all in different locations. So that's why we went through and created these common areas which we patched with different materials just to kind of do a kind of direct comparison from one material to the next. And we thought we'd get some better information on that. And again, these repairs were done kind of in the idea of not as a kind of professional, I shouldn't say professional, but I should say as a contracted type of work. It was more as what could be done by maintenance crews when they noticed that there was a partial depth repair need, and to kind of look at it as a less of a number of years that we'd expect, but to see how those materials held up in that way. And this we worked with industry on to develop kind of the method we were going to place these materials and the materials that we actually used. So a little background on the study and how it was developed. Anything else, Justin, you think of while I was talking there?
Nope, I think that sums it up pretty good. It was kind of a, some of them were placed by the manufacturer suppliers, some of them were placed by MnDOT personnel. And in the report, and it goes to, I guess, what you said, Ben, some of these have very, I don't want to say special tools, but I think everybody pretty much has a revolving drum mixer that they can pull behind their truck. And some of these products cannot be mixed in that. So that's one thing we're looking at is, do you have to go buy what I call a mortar mixer? Can you use that revolving drum that most people seem to have? That type of thing. And what type of tools does it take to put it down?
Right. And I think part of your final report will also be the placement and those types of issues that were encountered, not only the long-term performance.
Sorry, you broke up there, Ben.
Your report will contain the long-term performance of these patches, but it'll also contain the initial, how the ease of placement and some different issues, or if it was easy or not, during that installation of the material.
Correct.
Okay. I guess with that, we can, if no other questions or comments, we can move on to the next presentation. Why don't we transfer over? Thanks, Justin, for your time. And our last presentation, which is a little early, but I think we get started. It'll be from American Engineering Testing, and Derek Tompkins will be talking about the cold central plant recycling effort that was done on our low-volume road. So with that, Derek, once the presentation's up and ready, you're welcome to begin.
Thank you, Ben, and thank you. Good afternoon, everyone. Just getting this up right here.
All right, your microphone sounds good.
As soon as it bumps to the full thing, we'll be ready to go here.
Yep, we see it.
Okay. So again, my name is Derek Tompkins. I'm with American Engineering Testing, and I'm here to present a little bit about what we've done on the CCPR study. This is a longer-term study, and so what I'm going to be talking about today, we've talked a little bit about before. So I'm going to kind of try and keep it quick and just give you some highlights of what's been done so far. The objectives of the study are to learn more about what NRRA members want to know about CCPR in terms of practice, costs, and any needs that they see in their agencies, organizations, and then also in companion with the test cells at MnRO to perform a laboratory testing here at AET, and also AET will perform analysis of the field data that MnDOT and MnRO collect from their CCPR test cells, and we'll summarize that performance, and then we'll produce technical briefs kind of summarizing the state of the practice, the cost, and characterizing the performance of CCPR in terms of field performance and lab testing. An important, kind of feature of this whole thing is, this is the advantage of NRRA is we really want input from agencies on this work. So one thing that we've done is kind of reshuffle the tasks after the first 4 minutes or 4 months of the project. I worked with the TL, Dave Van Dusen, to kind of reorder the tasks so that we could maybe get some input from NRRA members on their opinions on CCPR, or some things that they like to know about CCPR, or if they're even interested in CCPR, applications that they could see for the technology. So we moved the survey up in the project work so that we could get some input from folks. And pretty soon here we'll be getting, as part of the Task 1 work, we came up with a draft survey that was reviewed by the TAP, and we'll distribute that to the NRRA members here in a few months. The red line in this slide designates where we're at in terms of the Gantt chart. So, and so as we go through, we'll be evaluating test data from the field, from the lab, and then we'll be developing these technical briefs. The idea being, I think a good thing to come out of this project isn't just the data and the analysis, but also give NRRA some deliverables, some research products that they can distribute. Because one thing that we've learned, and I'm going to discuss in a later slide, is that there's not a lot of CCPR-specific literature. There's the big study everybody knows about that Virginia DOT did at NCAT, but that's kind of it's a really kind of a boutique example. It's kind of a novelty. We wanted to give something. Hopefully, this study will give something a little bit broader that agencies can kind of latch onto and maybe see their own applications in the work that NRRA will do in this study. So the few sections at MnRO, I think we've talked about these before. There's 4. 2 have engineered emulsion, and 2 have foamed asphalt, and then 2 are surfaced with a double chip seal, and 2 have 1.5 inches of a hot mix. Some early performance are from these cells this spring. The engineered emulsion double chip, this is just kind of showing you photos that we've gotten from MnRO, is holding up. However, I think this has been shared earlier. The foam section with the double chip had some issues, but a month later, it's as good as new. And one thing that we've gotten from these cells is some writing data that Dave Van Dusen recently provided. And you can see that in October 2017, these are the empty symbols at the bottom, where we don't have a lot of writing. And then the progression of rutting, and we've seen more rutting in general in the foams sections, and that agrees with the testing that we've done in the lab so far on the field mixes we've done. We just completed the Hamburg. We don't have formal results ready, but the test has been run, and apparently the foamed mix was failing around 3,000 to 5,000 passes, whereas the engineered emulsion was holding up for anywhere between 7,000 and 9,000. So that kind of general rule of thumb agrees with what we see in this data. And again, as I said, for task one of the things we did was we reordered the task schedule so that we could get NRA input on the ongoing work, rather than, a lot of times what happens in research projects is the researchers go off and they disappear for 2 years and they produce a bunch of, deliverables and without really any input. They're kind of in a vacuum, and then they come back and give them to the TAP, and TAP says, well, did you look at this? Did you look at this? Did you look at this? And by that time, it's too late. You've used up all your time, and there's not a lot you do. So hopefully we can avoid that issue, and we can give people something that they want to see and something that answers their questions and concerns. So again, we went over the task plan. We went over the testing plan with the TAP and modified the plan according to their input, finalized it, and then got ready to build specimens. During task one, we also performed a literature review looking at CCPR. And a lot of the literature in this field is generally on cold mixes in general, and we wanted it to be a little bit more specific. As I said, there's the Virginia DOT study, and then there's just basically we had to look at agency paving specs. Nevada was one of the first adopters of CCPR. We looked at some industry guidelines. ARA has something. Also, there's a firm out in California called Pavement Recycling Systems, and they did a lot of the early they were an industry leader in CCPR and a lot of cold mix technologies in general. And so they had some documents that were helpful, but again, there's not a lot on this. It's that's really, talk about CCPR from the ground up. So we wanted to maybe use this project as a way to build some of that with the technical briefs that we'll put out later in the project and the final report. Here you can see the test plan. I mean, this is, again, we ran this past the TAP. We've built all our specimens up, and we've conducted the Hamburg wheel. So the other 4 are on the docket now, and we'll be proceeding with those this week and past the holiday. And we should have, finished results before the end of the year for all the tests. And again, I don't know, hopefully everyone can see the slides, but if you can't, we've got Hamburg wheel riding testing plan performed. We're going to do E-Star, we'll do DCT, SE, and indirect tensile testing. One thing that we might do with the ACB that we still need to kind of discuss is AT developed kind of an alternative to DCT for cold mixes, because they have a tendency to fail, not really give you good information in DCT. So there's a low temperature SCB procedure that we developed that we might implement here. We're going to talk that over with the TL and find out if he feels that's appropriate. And these are just slides mainly for the benefit to have pretty pictures. I'm pretty much done here. And also to reassure everyone that the work is proceeding. Here you can see gorgeous pictures of materials in our lab. And here we are prepping. We've got all our specimens prepped for testing, and here they are getting beat up on in that Hamburg wheel. And that brings us to the end. If you have any questions, please ask them. Otherwise, thank you, NRA, for your support, and thank you, everyone, for your time.
Thank you, Derek. Any questions there for Derek?
I don't have any online, and I don't have any in the classroom.
Dave, do you have any questions there? Anything you want to add? Dave Van Dusen? Not sure if you're available or not. But again, I think more will be coming from the study over the time. Again, it kind of points out the whole push for, Eshan mentioned it earlier. Derek mentioned it also here, saying that we do need some responses back to surveys if these studies are going to be up to their potential that they expect to have.
Steve had a question about the timeline for getting all the lab work done.
Dave Van Dusen?
Yeah.
Yes.
Well, I mean, we're right now. It's getting tested, so the Hamburg is moving along, and then we've got 4 that just one after the other. So definitely by the end of the year, I can't say exactly when, but it's getting done. Yeah, well within schedule. I think we had until, sometime in the fiscal year 20 to finish up the testing, so we'll be well ahead of schedule on this. And of course, if I'm talking to Dave Van Dusen, if you're out there, you're welcome to call me and ask.
Yeah, Dave mentioned thanks for your response. Any other questions out there? I guess with that, we'll conclude our presentations on the long-term research efforts that are being done from NRRA.